Okay, we're looking at relative velocity. So, what are we talking about when we talk about relative velocity? What I want to do is first up is just give you a simple way of looking at this. And let's have a few different objects here. Let's call this object A, let's call this object B, let's call this our reference point. Now, if A has a velocity, we'll call it, let's call that 1.5 meters per second to the right. Now, if B's velocity is 3 meters per second to the right, what are we measuring those relative to? Well, we're measuring those relative to the ground over here. You've got to have some point to have velocity measurements that you've measured them relative to, and everything in the universe can be measured relative to that. Now, in physics we might want to know, well, what's the velocity of A relative to B? And we'll say it that way. What's the velocity of A relative to B? So B here, the one we've ringed here, the one we've said relative to, is the one that for all intents and purposes is going to be still. So when we say V's velocity relative to A, sorry, A's velocity relative to B, what we're talking about is as if suddenly B's velocity is 0 and we're now asking what's everything else's velocity. And the simplest way to get that is just to subtract B's velocity off everything. When we do that, it's a vector subtraction. We find that B now has a velocity of 0 meters per second because we've just subtracted its velocity off. And A would have that 1.5 minus 3 will give it a velocity of 1.5 meters per second to the left, or a minus 1.5 if you like. So we've said velocity of A relative to B is 1.5 meters per second to the left, or negative. So it's as simple as that when it comes to finding out relative velocities. And you can do it, this was in one dimension, but of course you can do it in 2 dimensions. Just as easy. Just add the negative vector for that velocity you want to find things relative to, in this case B, to everything. That thing's velocity will then become 0, and you'll see what the velocities of everything else are relative to it. So that's a nice simple way of looking at it. Now, a few things I want to make clear before I go into the next bit is, if you've got VA relative to B equals minus 1.5 meters per second, then you can say VB relative to A is equal to 1.5 meters per second. So when you rearrange these guys, put them around the other way, you just change the sign on the magnitude. What we're basically saying there is if A's velocity relative to B is minus 1.5 meters per second, then B's velocity relative to A must be plus 1.5 meters per second. So that's the simple approach to this relative velocity. What if we've got a situation though, like we had in one of the problems I gave you, where we've got a girl walking on a plank? We'll give her some arms. We can call her A, and we'll call the plank B. Now, we could give you a relative velocities for those things relative to the ground, or we could give you the relative velocities relative to each other. What if we say the relative velocity of A relative to B, since she's going in that direction, right, then relative to B is if B is still, it's going to be a positive velocity, so it's, let's say it's 1.5 meters per second. Quite fast, really. Then we know immediately that velocity of B relative to A is minus 1.5 meters per second. But we actually want to know the relative velocity to the ground, maybe. We have not said anything about that yet. So what if I wanted to know VA relative to the ground? Or I could ask for VB relative to the ground. Now this brings in another little technique that we need to talk about. If you've got, and we'll do this a little bit separate, maybe just here, just put that off to one side, we'll come back to that. If you've got V and you want it relative, velocity of A relative to C, this is different, and you've got VA relative to B, and you can find the velocity of B relative to C, then if you add VA relative to B plus VB relative to C, you will have velocity of A relative to C. It's as if these little guys in the middle here can cancel out. And if you can combine that with that other little rule we already had, which was that if you have VBC, then you know that VCB is equal to negative of VBC. So if you turn the little letters around, you just put a negative on it and all is okay. So based on that, we can then write our little vector equations for figuring out stuff like this. So if I wanted VAG, you know, I'm just making this up as I go along. If I wanted VAG, then I'm definitely going to want VA relative to something, and in our concerns all we've got is A and B. So I write that as a B, and I can then say I would definitely want these little guys to cancel out, so I'm going to want VBG. And then I know that that would give me the vector equation I'm looking for. Now, what we do have here is we definitely have VA relative to B. That was 1.5, so we could actually say that's 1.5 meters per second. And we can actually say VB relative to ground and VA relative to ground. So we need to get some sort of information to help us with that. And at this stage, I can't immediately solve that. We just know their relative velocity relative to that. But this is where, if we've actually done our equations from the conservation of momentum, the fact that the velocity of center of mass stays the same if there's no external force, then we should be able to put in a substitution here from somewhere. So if I've done this one where I've got the M1V1 plus M2V2, now if the velocity of the center of mass is staying the same, then we should be able to make that all add up. So if we know the velocity of the center of mass was 0, or whatever it was, M1 and M2 equals the velocity of center of mass, we can use this little equation here. We can solve that little equation to give us one of these other guys in terms of the other guy. And when we make that substitution, we should be able to make it all work. Alright, that's all I wanted to show you.